To finish with our study of integration via partial fractions, we're looking at the case where we have repeated irreducible quadratic factors, and as we will see, this can get pretty nasty. So if the factorization of the denominator contains a repeated irreducible quadratic factor, something of the form ax squared plus bx plus c to the n, where ax squared plus bx plus c cannot be factored any further, which means b squared minus 4ac is negative, then the decomposition into partial fraction will contain the corresponding terms, a linear function over that irreducible quadratic factor, plus another linear function over that irreducible quadratic factor squared, and then we have one such term for each power of this irreducible quadratic factor, from 1 all the way to power n. So the problem becomes to integrate these type of terms, a linear function divided by an irreducible quadratic term to the power k. So how do we do that? Well, we pretty much follow the steps that we have outlined for the case where k is 1, in other words, for the case where it's a non-repeated term. But practically, it will mean a lot of complications. Specifically, we start with completing the square. So we factor out a, when we pull it out of the power k, we get 1 over a to the k, and then we have this x squared plus b over ax in which we complete the square. So we take 1/2 of the coefficient of x, so we get something that looks like that, where alpha is some alpha squared correspond to some positive term. It doesn't matter exactly how it is in terms of a, b, c. And then we take the substitution u equal whatever is under the square, and we get something that roughly looks like that, a linear function in u over something of the form u squared plus alpha squared to the k. In this, we're going to do what we've done again in the case where k was 1, that is, split the fraction. On one end, we're going to need to integrate u over u squared plus alpha squared to the k, and on the other end, 1 over u squared plus alpha squared to the k. In the first case, we can proceed as before. At the top, we have u du, and at the bottom, we have a power of something of the form u squared plus alpha squared, whose derivative is 2u du. So in other words, if I set v equal u squared plus alpha squared, I get 1/2 integral of dv over v to the k, and that can be integrated. So we have no problem with this part. The problem starts with this other part. In the case where k was 1, we had a formula with arctangent to integrate this. However, now we don't have this formula available, and what we need to do with that is use trigonometric substitution. And as you know, this can be quite long and require a lot of calculations. We've done such an example at the end of the videos, instructional videos on trig substitution in Module 5. So what do we do in this case? Well, we're going to use a trig substitution. U is alpha tangent of theta, then du is alpha secant square theta, and we substitute. So at the top we have du, that's alpha secant square of theta. At the bottom we have u square is alpha square tangent square theta, plus alpha square, all that to the k. I can pull out the alpha square, and when I pull it out of the power k, I get alpha to the 2k. I can pull out the alpha that is at the top. I get a constant term, alpha over alpha to the 2k, and then the integral of secant square divided by tangent square theta plus 1 to the k. And the point of this trigonometric substitution is that tangent square theta plus 1 is really just secant squared of theta. So at the bottom I really have secant of theta to the power 2k. So in other words, after simplification, what I'm integrating is 1 over secant to the 2k minus 2, which I can write as cosine theta to the power 2k minus 2. And now it comes down to integrating an even power of a cosine or a sine, and we've seen how to proceed with that using the double angle formula in module 5, at the beginning of module 5. So specifically we're going to write that as a power of cosine square theta and replace cosine square theta using the double angle formula by 1 plus cosine of 2 theta over 2. Then you multiply things through and potentially iterate this process until you have no powers left. So if k is large, this can be quite painful, and additionally at the end we get a function of theta and we have to go back to a function of u first and then as a function of x. So this is a fairly long process potentially. We're going to look at a couple of examples. First, we're going to look at an example where we're lucky and we don't really have to worry about this trig substitution. And then we'll look at a case where we need to do the trig substitution, and that will illustrate that it is theoretically always possible to do it, and practically quite difficult if you have to do it by hand. So let's look at the integral of the function 1 minus x plus 2x squared minus x cubed, all this divided by the product of x with x squared plus 1 squared. The degree at the top is 3, the degree at the bottom is 2 times 2 plus 1, so 5. So the degree at the bottom is higher, so we don't have to worry about long division, and we can just write out the form of the decomposition of this function into partial fractions. In this case, the factored form contains one non-repeated linear factor, x, and to this corresponds a over x. Then we have one irreducible quadratic factor, x squared plus 1, that is repeated twice. So we get two partial fractions, bx plus c over x squared plus 1 and dx plus e over x squared plus 1 squared, one for each power of x squared plus 1 from 1 to 2. And now we need to find these coefficients a, b, c, d, e, and to do that we're going to rewrite the right hand side as one fraction and identify the numerators. So if I multiply things through, you see that to write the right hand side as one fraction with denominator x, x squared plus 1 squared, I need to multiply top and bottom for the first term by x squared plus 1 squared, so I get a x squared plus 1 squared. For the second fraction, I need to multiply top and bottom by x and by x squared plus 1. That's why I get bx squared plus cx times x squared plus 1. And for the last one, I need to multiply top and bottom just by x, so I get dx squared plus ex. So now we can identify the numerators, and I just multiply things through in x squared plus 1 squared, and then look at what I have for b. Bx squared is multiplied by x squared plus 1. In other words, b is multiplied by x to the fourth plus x squared. Similarly, c is multiplied by x cubed plus x. And now I can reorder the terms to look at the monomes of each degree, right? What is the coefficient of x to the fourth, of x cubed, of x squared, and so on, and identify the coefficients of corresponding degree, since we have an equality between two polynomials. So if I do that, the coefficient of x to the fourth, you see that it is a plus b. We have only one term in x cubed, it's cx cubed. And for x squared, we have 2a, b, and d. As for x, we have cx and ex, and the only constant term is a multiplied by 1. If now we identify the coefficients of corresponding degree, we see that a plus b should be 0, c should be negative 1, 2a plus b plus d should be 2, c plus e should be negative 1, and a should be 1. So these are the conditions. You see that a is 1 and a plus b is 0, so b is negative 1. C is negative 1, and therefore we can also find d and e, because d is now 2 minus 2a minus b, and we have found a and b, and e is negative 1 minus c, and we have found c. So this way we find a is 1, b is negative 1, c is negative 1, d is 1, and e is 0. So that means that we can replace the coefficients by these values in our decomposition into partial fraction, and this is what we obtain: 1 over x plus negative x minus 1 over x squared plus 1 plus x over x squared plus 1 squared. And so this is what we want to integrate. One of the steps that we indicated in how to deal with these types of partial fractions was to split the fraction whenever possible. So this negative x minus 1 over x squared plus 1 is split into negative x over x squared plus 1 minus 1 over x squared plus 1. And now we're going to use the change of variable u is x squared plus 1 in order to integrate the second and fourth fraction in this sum of 4 fractions. So in that case, du is 2x dx, so we're going to replace x dx by 1/2 du. And so we obtain, for the integral of dx over x corresponding to the first fraction. Then we have minus 1/2 of the integral of du over u minus dx over x squared plus 1 plus 1/2 integral of du over u squared. So for the integral of dx over x, we get just natural log of absolute value of x. Here we're going to get negative 1/2 natural log of absolute value of u. For this fraction, we can use our formula with the arctangent. Here, this is really just arctangent of x. And for this last term, we have the integral of u to the negative 2. So we get u to the negative 1 over negative 1. In other words, negative 1 over u, that we multiply by 1/2, it's going to give us negative 1 over 2u. So this is what we obtain, and u was x squared plus 1, so we can just replace it, and we obtain explicitly our antiderivative of the function. So this was not too bad, and specifically was not too bad because the coefficient e was 0, so the particular term where we would have to use trigonometric substitution disappeared. Now let's look at an example where it's not the case. So we start with really one of the terms in a partial fraction decomposition. So it's already a partial fraction. So one of these simpler terms, right? Supposedly. But this is the case where we have just a linear function over the square of an irreducible quadratic term. Indeed, this is an irreducible quadratic term because if you calculate b squared minus 4ac, you get 1 minus 4, negative 3, you get something negative. So we cannot factor that any further. So in that case, if we follow the steps we've indicated, we would start with completing the square at the bottom, which means that we look at x squared plus x and we identify that with x plus 1/2 of the coefficient of x, in this case 1/2, that we square, and then we subtract this square of 1/2. So in other words, we obtain x plus 1/2 squared minus 1/4 plus 1 inside our square at the bottom. Of course, 1 minus 1/4 is 3/4, so this is what we obtain. And now the next step is to make a substitution where u becomes whatever is under the square. And then we're going to have to replace x plus 1 in terms of u as well, but if u is x plus 1/2, then that means x is u minus 1/2, so when I add 1, I get u plus 1/2. So we obtain u plus 1/2 over u squared plus 3/4 squared. Then we split the fraction, as we have already done. It's u over u squared plus 3/4 squared plus 1/2 of 1 over u squared plus 3/4 squared. And so now this is what we need to integrate with respect to u. The first term is not going to be a problem because we can proceed by substitution. We let v be u squared plus 3/4, then dv is really just 2u du, so what we have at the top, u is, well, this u du is 1/2 dv. So we end up with 1/2 integral of dv over v squared plus 1/2 integral of du over u squared plus 3/4 squared. The first term is not the problem, but the second one is one of these cases where we need to use trig substitution. So this is where we're going to have some serious work to do. So we have a sum of squared, right? U squared plus a positive number. And so we're going to use a trig substitution u equal a tangent of theta, where a is the root of this positive term 3/4. So namely, u is going to be square root of 3/2 tangent theta, where theta is restricted to the open interval from -π/2 to π/2 to make sure that tangent is 1-to-1 on that interval, and we'll be able to use the arctangent. Then du is √3/2 secant squared of theta, so we can replace du by this quantity and u squared by 3/4 tangent square theta. Pulling out the √3/2 from the du, this is what we obtain. You see that here I wrote explicitly what the integral of dv over v squared is. Of course, this is the integral of v to the -2, so you get v to the -1 over -1. In other words, -1 over v. When multiplied by 1/2, you get -1 over 2v. Then we have 1/2 multiplied by √3/2, and then we have a secant squared at the top, and at the bottom, inside the parentheses, 3/4 tangent squared u, which is u squared, plus 3/4, all that squared. Okay, now if I replace v by its value, v was u squared plus 3/4, and I replace u by its value, so now 1/2v is really 1/2 times x plus 1/2 squared plus 3/4. On the other hand, when I multiply 1/2 by √3/2, I get √3/4. And then if I pull out the factor 3/4 outside of my square, I get 9/16. And inside the parentheses, I now have tangent square theta plus 1. And the whole point of this trig substitution is to get this expression tangent square theta plus 1 to appear, because this is equal to a square, namely the square of secant theta. What we have inside the parentheses in the first term is really the form where we have completed the square of our original irreducible quadratic term x squared plus x plus 1, so I can rewrite it that way. On the other hand, if I pull out the 1/9/16 and write it as 16/9, I can pull that in front, and then I have secant square theta at the top, and at the bottom I have secant square theta squared, in other words, secant theta to the 4th. So that cancels out as 1/secant square theta, but since secant is 1/cosine, what we have is really just cosine squared. So this is what we obtain after cancelling this 16/4 as just 4. So we have now an explicit part of the function plus a constant times the integral of cosine square theta, and we know how to integrate that. Namely, to integrate an even power of cosine, we're going to use a double angle formula and replace cosine square theta by cosine 2 theta plus 1/2. After pulling out the factor 1/2, we're going to obtain, for an antiderivative of cosine 2 theta, 1/2 sine 2 theta, and for an antiderivative of 1, just theta. Of course, when I pulled out 1/2, I obtained a 2 instead of a 4 in the multiplicative constant in front. Now this sine 2 theta is a little bit of a problem, because we want to, at the end, obtain a function of x alone without any theta left, because we're looking for an antiderivative of our original function of x, and we want that as a function of x. We have a clearer correspondence between theta and u than between 2 theta and u, so I'm going to replace sine 2 theta by 2 cosine theta sine theta. But since I'm multiplying by 1/2, what I obtain is really just cosine theta sine theta plus theta. And now we need to look into transforming things back in terms of x. So we look at the trig substitution we've done. We had u equal root 3 over 2 tangent theta. In other words, 2 over root 3 u is tangent theta, or theta is arctangent of 2 over root 3 u, because we are in the proper interval for theta to apply the arctangent. And what does that mean in terms of cosine theta and sine theta? Where we're going to use the type of geometric representation we have used to go back to the original variable when we were looking at trig substitution. Namely, we see that since tangent theta is 2u over root 3, that means that the ratio of the opposite side to the adjacent side in a right triangle is 2u 2 root 3. Using the Pythagorean theorem, we see that the missing side would be root of 4u squared plus 3, but u was really just x plus 1 half, so we can replace u squared by x plus 1 half squared, and multiplying things through here we obtain root of 4x squared plus 4x plus 4 for the hypotenuse. Now cosine will be the adjacent side root 3 divided by the hypotenuse root of 4x squared plus 4x plus 4, and sine will be the opposite side 2u, which we can write as 2x plus 1 because u is x plus 1 half, divided by this same hypotenuse, which is root of 4x squared plus 4x plus 4. So we obtain this expression where I multiply root 3 and 2x plus 1, and each one have these same denominator root of 4x squared plus 4x plus 4. So when we do that, we end up with this expression because, of course, the product of the denominators end up being the square root squared, in other words, whatever is under the square root. We could simplify that a little bit further with the constants and so on, but here we have an explicit function of x as an antiderivative of our function x plus 1 over x squared plus x plus 1 squared. Now keep in mind that here we started directly with one single partial fraction to integrate. In general, it could be that we have several of these to deal with. So when the irreducible quadratic term is repeated many times, things get technically difficult, even though theoretically there is a systematic way to deal with them. So now that we have gone over all the different cases, it is time for you to do some homework.